This is Algebra 1 Common Core, and today we're going to talk about precision and significant digits. So, precision is the level of detail in a measurement. A measure is considered more precise than another measure if that measure has a smaller unit. Right, so let's go over a few examples. So between 3.6 and 352 centimeters, what we're first going to do is convert one measurement to the other. So it's easier to convert centimeters into meters by dividing by 100. So what I'm going to do is to divide 352 by 100, I take and move it 2 decimal places because there are 100 centimeters in 1 meter. So 3.6 meters and 3.52 meters is what I'm comparing. Now, they both have, I've converted them both to the same unit, so right now they're both the same unit. So what I'm going to do is I'm going to compare how many digits each number has. So this one only goes out to the 10th digit, and this one goes out to the hundredths. So the more precise measurement is this one because it extends to the hundredth unit right here. Okay. Now for our next comparison, we have 5.68 miles and 5.5 miles. So again, the units are the same, so I'm going to choose the measurement that goes out to the furthest amount of digits to the right of the decimal. So this one's more precise because it goes out to the hundredths, whereas this one only goes out to the tenths. Okay. Now, this is a funny comparison because, as you know, 12 inches is equal to a foot. But since inches is smaller, a smaller measurement than 1 foot, 12 inches is considered more precise than 1 foot. Okay, so that's how we can make, that's how we can compare the level of precision for each measurement. Now, when we talk about significant digits, there's a few rules that we're going to go by. Okay, first of all, the first rule is that any non-zero digit is significant. So for instance, when I say digit, by the way, I mean a number inside of a larger number. So the digits in 37.85 are 3, 7, 8, and 5. Okay, so 5 is the digit in the hundredths place in this number here. That's what we mean by digit. Okay, so this number has 4 significant digits because there are 4 non-zero numbers here. 1, 2, 3, 4. 622 has 3 significant digits. Okay, now we're going to go over our rules for zeros. So if a zero is between any 2 significant digits, then the zeros are considered significant. So remember, 8 and 6 are significant because they're non-zero digits. So a zero in between these are significant. Okay, so 9 and 7 are significant because they're non-zero. So these 2 zeros would also be considered significant. So there's 4 significant digits. Notice that this placeholder right here, this 0 in the 1 spot, is not a significant digit. Okay, the zeros at the end of a number to the right of a decimal place are significant. The way that I think about that is, if someone put them there, then they intended that the measurement actually, so instead of it, if I put the number 1.4, it's hard to tell whether the number is exactly 1.4 or if someone just rounded that. But if I put 1.4000, then I know the measurement is exactly 1.4000 because I put those digits there. That's what makes them significant. So a number to the right of a decimal point, zeros at the end of a number, so these zeros come to at the end of a number to the right of the decimal. So this has 1, 2, 3, 4, 5. The same one, this has 3. Okay, zeros to the left of the first non-zero digit in a decimal are not significant. So this is the first non-zero digit. These zeros right here are to the left of it in a decimal, so they are not significant. So the 7 is significant by rule 1, and the 0 is significant by rule 3. So if I just name these rules, it'd be easier to understand it. Okay, these 3 right here are not significant. Likewise, the 1's not, the 1, the 4, and the 8 are non-zero, so there are 3 significant, and this 0 is in between 2 non-zero digits, so it's significant. Zeros at the end of a number without a decimal point are assumed to be not significant. So these numbers right here, these zeros right here, are not significant. So 4 and 5 are significant because they are non-zero. There's a 0 in between two non-zero digits, so this 0 right here is significant, but none of the ones to the right are significant. And same with this. So this has 4 and this has 2. Okay, so let's use those rules to determine whether or not we have significant digits here. Okay, so what I did was I just copied this chart right here so I can use it as a reference. And you know what I'm going to do is I'm going to write rule 1, 2, 3, 4, 5, and then I can reference which rules I'm using. Okay, so in this next one we at least have 2 because the 6 and 3 are non-zero. If a number, so this 0 right here by rule 4 is not significant because it comes between, it's on the right of a non-zero number in a decimal. So right here we just have 2 significant digits, okay? And that's a combination of rule 1 and rule 4. Okay, so here we have 3 non-zero digits, and we have a 0 in between 2 non-zero digits, so we actually have 4. So that's a combination of rule 1 and rule 2. Rule 2 says that there's a 0, if there's a 0 in between 2 non-zero digits, then it's significant. Here, so let's count the non-zero digits, 1, 2, 3. Okay, this 0 is in between a non-zero digit, that's by rule 2. And these zeros are to the right of a decimal point, so they are actually also significant by rule 3. So we have 1, 2, 3, 4, 5, 6. This has 6 significant digits. Here we have 2 significant digits, so at least they're 2 by rule 1. Now these zeros by rule 4 are not considered significant, so here we only have 2 significant digits. Okay, so one last thing we have to go over is what happens when we add and subtract numbers. What happens, what happens when we operate on numbers and we want to keep the same level of precision. So this happens a lot in science. You know, when students ask me, well, what do we round to? This is a nice rule in order to figure out what you should round to if you aren't given any restrictions in the problem. So let's say a rectangle measures 15.6 centimeters on one side and 18.67 centimeters on the other side. What is the perimeter to the correct number of digits? So the perimeter of a rectangle is 2 times the length plus 2 times the width. So here we have the perimeter is equal to 68.54 centimeters. Okay, so let's read our rule here. Addition and subtraction, the sum or difference must be rounded to the same place value as the last significant digit of the least precise measurement. Okay, and the product or quotient must have no more significant digits than the least precise measurement. So actually what we're going to do is go by the addition and subtraction, because here we have this number and we added it to this number to get 68.54. So let's think about this. We have to go to the same place value as the last significant digit of the least precise. So here the one that was least precise was actually this one, because this only went to the tens place. So I want to, this has 3 significant digits. So I want my perimeter to also have 3 significant digits. That means that I have to get rid of the one in the tenths place here. Okay, or the hundredths place. So it's going to be 68.5 centimeters, because there's my 1, 2, 3 significant digits right here. So that right here matches this level of precision. Okay, and I remember, again, I just rounded it. 4 makes this number in the tenths place round to, or it keeps it at 5. What is the area? So the area we know is just the length times the width. Okay, and so my answer here is 291.252. And I sort of made a mistake in my explanation for the perimeter problem. So let's just look at the addition and subtraction rule again. It has to be the same place value as the last significant digit of the least precise measurement. So 15.6 was the least precise measurement. The last significant digit ended up in the tenths place. So I needed my answer to end up in the 10th place here, which is what it did. I accidentally counted the significant digits, which is not what you're supposed to do. That's actually the rule for multiplication and division. So here, the product or quotient, because I'm multiplying two numbers together here, must have no more significant digits than the least precise measurement. So again, the least precise measurement was 15.6, which had 3 significant digits. So here, this can only have 3 significant digits. So that means I've got to cut down all the significant digits down here, because these numbers right here are going to have to be, I'm going to have to put 1, 2, 3 significant digits here. So here, oh, and by the way, this is in centimeters squared, right? Because we're multiplying centimeters by centimeters. So here, let's round it to the nearest centimeter squared. That's a 2 right there, so it's going to remain at 291 centimeters squared. You do not want to put like a 0.0 here, right? Because if you put a 0.0, then that 0 would actually make it to have 4 significant digits, so be very careful. The answer here is just 291 centimeters squared. Right, so I count the number of significant digits in the least precise measurement. Here I go to the place value of the least precise measurement here. Okay, and that's it for today.